research that has been keeping me awake for the last, geez, I don't know, 3 years. This research really started as a small undergrad project, and then became my honors, and then ended up encroaching a little bit into my master's project, which was on a different dinosaur. But it's been many years in the works, and I'm very glad to finally get this out there. So just a little bit of some background. My paper is on Heterodontosaurus, and I just want to give a very brief intro on Heterodontosaurus and why it's important. So there are 3 flavors of dinosaurs. There are sauropods, which are long necks, theropods, which are meat eaters traditionally, and birds. And then there's the objectively best group of dinosaurs called the ornithischians. And Heterodontosaurus is the basalmost member of Ornithischia. It's not only is it one of the oldest members of this group, but it's consistently recovered in various phylogenetic analyses as the basalmost member of this lineage. Because of that, it has, a disproportionate importance in understanding the evolution of this group and dinosaurs in general. So even before our study, this was an already important taxon. So this is the study specimen. This is AM4766. And when Jonah showed this to me, he was like, hey, have a look at the specimen. It's pretty cool, right? I'm freaking out. I'm like, holy crap, look at this. This is stunning. And then he points out a few things to me in the specimen. He's like, okay, we've got these weird little platey things over here. There's these little jobbies on the other side of that block. And then we've got these little gastralia running down here. So, it's like, what the hell's going on? We can see the stereotypical sort of dinosaur skeleton, but like, what are these like other weird little bits? What are these like cornflake pieces and stuff? And these other little gastralia and these little other nubbins of bone. And when your question is what the hell is going on, the answer is stick it in a synchrotron. And that's what we did. And then reconstructed the anatomy from that. So here's a quick video of what we found. So the specimen was divided into multiple blocks. Each of those blocks was sort of scanned individually or simultaneously and then split afterwards. But this was the largest dinosaur and largest species in general to be scanned at the synchrotron and at this resolution that we scanned it at. Which is great because now instead of having spitting skulls, we've got spitting whole bodies minus tails. So the color bits are what I have segmented so far of the specimen. And in addition to, you got the green and blue, your vertebral column and the ribs. But the really interesting things are those little purple bits behind the red forelimb and the yellow tiny little riblets that are running from the chest to the pelvis at the back. The pelvis is that golden strap-like collection of bones. So this is a representation of the specimen and the digital works that I extracted from there. So I remember when I first got the specimen, John was like, okay, cool, we've got these things and it's got gastralia. So I went home and I read a paper about dinosaur gastralia. Became a huge fan of Leon Claeson's, and that's a different story. I embarrassed myself at SVP about it. It's hilarious. But then, in the paper, there's like a little subsection about ornithischian gastralia, and it's just the opening sentence is gastralia have never been found in ornithischians. And the day before reading this paper, I was holding an ornithischian with gastralia, and that's when alarm bells started ringing. I was like, holy shit, we've got a world-class specimen on our hands here. So we've got this new anatomy, and it includes gastralia, which is these little thin blue bones at the bottom, sternal plates, sternal ribs, and these are all pieces of anatomy that are implicated in various ventilatory mechanisms in a variety of other animals. This includes things like birds, crocodiles, squamates, and some mammals as well, except the gastralia bit. And this is a video of gastralia, sternal ribs, and the sternum in general. kind of all working together to change the shape and volume of the body in crocodiles to facilitate ventilation. Ventilation is just is how you move air through the lungs. So you can see the whole body collapse as bits of the belly and the chest compress and expand. And that, together with the crocodilian hepatic piston, which is that mechanism that they use with their liver, it helps get air flowing through the lungs. I'll play that again in case anyone missed it. Okay, cool. So we've got these new pieces of anatomy in Heterodontosaurus. We can compare them to what crocodilians and other reptiles are doing, and we can reconstruct how Heterodontosaurus was breathing. It was using the gastralia and the sternal ribs and the chest all in harmony to try and really deform the body wall and change the internal volume of the body and facilitate changes in lung volume and drive lung ventilation that way. But what happens in more derived taxa? I hate the word, but like in this sense at least, but like what happens in its descendants? So Heterodontosaurus has these gastralia, it has these really, really specialized mobile sternal ribs, but more derived taxa don't have these features. In fact, one of the things that has traditionally been used to define ornithischians, apart from their unique pelvis, is actually the loss of gastralia. The complete lack of gastralia has been a synapomorphy of ornithischians. But in addition to not having gastralia, ornithischians in general, when they do preserve them, have very, very simple sternal ribs. I keep coming back to this point of sternal ribs because they're a really weird part of reptilian rib cage anatomy. And they are these bones in the salmon pink color. So in figure C, we've got like what the different sternal ribs of Heterodontosaurus look like. We've got 3 pairs, and they kind of look like little tennis rackets. And that the flat part of the sternal rib would have been where muscle attached and would have helped deform the chest. But all of those sort of modifications are lost in subsequent lineages. So there's this dinosaur called the Celosaurus, which preserves sternal ribs as well. And its sternal ribs are really unspecialized. They're really just flat and rectangular and don't have any of these little joints or expansions for muscle attachment. They're really kind of passive players in how the chest is working. So what happens in between Heterodontosaurus and things like the Celosaurus? Well, they lose ornithischians lose gastralia, but they simultaneously lose the sternal rib mobility. That means that they kind of lose a viable mechanism or a substantial mechanism of how they're getting air flowing through their bodies. Well, how do we solve this problem then? So this work is really built on the shoulders of many giants, but 2 papers in particular really help me connect a couple of dots and really make a lot of sense in this. The first would have been Emma Schachner and colleagues' work in 2011, which reconstructed the types of lungs that various archosaurs and dinosaurs in particular had. And you can do this by looking at how the ribs articulate with the vertebral column. There's some like technical anatomical foundation behind this, but safe to say it's pretty consistent when you apply this method to extant systems. It works out pretty well. And doing this work, she was able to identify that theropods and sauropods, long necks and meat eaters, had lungs that were almost identical to that of birds, and that they are fixed and rigid, and they don't deform like ours or like crocodilian lungs. What they did find, though, was that ornithischians have a heterogeneous lung, and that means that the anterior half of the lung is rigid and non-compliant. It kind of stays in place. It doesn't change any change. There's no change in volume of that region of the lung. But the larger posterior half of the lung is compliant and is a lot more like the lung of a crocodile, or analogous to the lung of mammals in that it actually does change shape and does change volume. In animals like sauropods, birds, and theropods that don't have a lung that can change volume, its volume, they have a series of air sacs that help get air into the lung instead. The second really important paper was by Leon Claessens, and it shows that crocs have two main ventilatory mechanisms. One is costosternal movement, so that's just a fancy word of saying the chest and ribs, and then visceral displacement, which is shifting the organs, and that's the hepatic piston model. The hepatic piston is kind of what you learn about in intro bio, with how the croc shifts its liver back and forth to change lung volume. So this is a pie chart, and I know Jonah hates them, so I like including it in talks just to trigger him. But crocodiles are weird in that they exemplify two ventilatory mechanisms that other lineages only pick one of, really. Crocs are an outlier because they're not actually ideal candidates to compare things to. But safe to say that the costosternal movement component of how crocodiles breathe is how squamates breathe. So I've got some Komodo dragons there to represent squamates. So they will swing their ribs and their chest bones back and forth, and that's how they get air flowing through the lungs. And then the second component to crocs is that they have this visceral movement and this visceral displacement. So they're shifting the guts and all the organs back and forth, and that's also helping shift air through the lungs. There are a few other components, like at the top over there, there's vertebral flexion, pubic rotation, and gastralial movement that all contribute minor ways to how air flows through the lung. But this is majority of the data is clear. There are two movements, two types of movement, and crocs have both of them. So squamates will use costosternal movement, and animals like mammals will use visceral movement, using their diaphragm, for instance. So costosternal movement is not possible in derived ornithischians because they lack specialized parts of the sternum. Their vertebral column is really simplified. Vertebral flexion is not a very good explanatory model either, or mechanism for ornithischians. They have these ossified tendons across the entire vertebral column that really rigidifies the whole structure. Their tails couldn't bend laterally, for instance, because of this trellis of tendons. Crocodiles are the only ones that really can rotate their pubis. So that's an impossibility for ornithischians. Of course, they lose gastralia as well, so that goes out of the window. So the only other mechanism that we could potentially invoke, and that any other animal, any other vertebrate uses to get air flowing, is invoking this muscular diaphragm-like sort of structure. But how do you find a diaphragm really, or evidence of a diaphragm? Well, weirdly, it's kind of all in the hips, and we identified a feature in the pelvis of ornithischians that is analogous to some features in crocodilians, specifically the location of the musculi diaphragmaticus, which is the crocodilian's diaphragm-like muscle. If you look at the top right figure, you'll see the crocodilian pelvis and then two bodies of muscle emanating from the pelvis, attaching to that orange liver that then attaches to the lung. That diaphragmaticus muscle, a substantial portion of it is actually located right and directly anterior to the acetabulum. Or it just so happens to be that immediately anterior to the acetabulum in the pelvis of ornithischians, that's the second figure, there's a structure called the anterior pubic process. So this bone in purple is the pubic bone, and the APP is this long projection. This projection also has some evidence of muscle scars on it as well. So some muscle was attached there at some point. And it is and those muscle scars are oriented in the anterior posterior direction. So what I wanted to do, and this is where Jonah's superior supervising kicked in as well. Was I wanted, I had this idea or this trend that I've been noticing in the literature that really, really early ornithischians have a tiny APP. So this region of the pelvis in purple is really, really small. And in very, very derived and extremely charismatic taxa, the APP is not only long, but it's also elaborated on in very specific ways. And so I combed through the literature, did a few museum visits, collected some data, and then we ran an R script, corrected for body mass, corrected for gait, a quadrupedal, bipedal sort of stuff. And then so we ran an R script correcting for those things. And we can clearly demonstrate that the APP really expands in very specific ways throughout ornithischian evolution. So at the bottom, you can see it in Heterodontosaurus, for instance. The APP is the smallest it is in the lineage. This is also when ornithischians still have gastralia and a very complex costosternal complex. But immediately after Heterodontosaurus, the APP begins to enlarge. And that's also simultaneously when gastralia are lost and the chest starts becoming a little bit more simple. Using all of this information, we propose a new sort of ventilatory mechanism for how ornithischians are getting airflow through the lung, and that's called the pelvic bellows model. And this is kind of a little bit how it works. Don't you just love a cute GIF? So this is a stepwise sort of progression of how this would work. The first taxon at the top there is something called Silosaurus. It's either the basal most member of Ornithischia, according to some new analyses, or it's just a very good dinosaurian outgroup. It's a dinosauromorph. It's not a true dinosaur yet, but it has no APP. It's got a very simple sort of stereotypical archosaurian pelvis, and gastralia are present. At this point, gastralia, in archosaurs at least, form a substantial portion of how they're getting airflow through the lungs. That's a whole different talk, but suffice to say that the gastralia kind of articulate like a series of scissors across the belly. And if you can imagine those scissors opening and closing, they'll be changing the shape of the body wall and changing the internal volume of the body. The second taxon is Heterodontosaurus, and it has a really, really small APP that you can see labeled over there. And gastralia are present, and the sternal ribs are present and still mobile, and are quite specialized. So the sternal complex is a major ventilator with the pelvic bellows as an accessory mechanism. Then in taxon C is something like the Celosaurus. This is, in quotes, an intermediate grade of ornithischian. And it has a really elongate APP. Its sternal ribs become fixed and immobile. Gastralia are absent, but the abdominal musculature is still involved hypothetically, at least still involved in getting airflow through the lungs through stomach contractions. This is similar to what the primitive archosaurian condition is, just minus the gastralia. But the pelvic bellows is a substantial ventilator in this model, and this is probably the point where the pelvic bellows becomes the major driving mechanism. And then in hyper-derived, quote-unquote hyper-derived taxa, like this Corythosaurus over here, the APP is not only elongated, but it's also deepened. It's a little bit exaggerated. In ornithopods, it gets really deep and clabate like this. In ceratopsians, it kind of looks a little bit like an inverted Dorito, like it kind of flares out anteriorly in a triangular sort of shape. In these taxa, the sternal ribs aren't preserved even in mummified taxa or mummified specimens. Gastralia are still absent. And here the pelvic bellows is going to be the major ventilator. So, after, all this work and, whatever, it's been really fun to actually get this research out there and see the media sort of play around with it. This is by far my favorite title. no, this dinosaur isn't vaping, it just breathed like a weirdo, which is simultaneously a shot at my artwork and my research. So that's a 2 for 1. And then I've been using my own lungs to prattle on about this elsewhere as well. So I did a radio interview in the wee hours of the morning, I think at 2 a.m. my time, on SAFM. And then again, when I was in the field, I got called for another interview for Radio 786. And this was a really fun interview, actually. This was a pretty cool one. I woke up to the call from the producer saying, "Hey, are you ready to go in 10 minutes?" And whatever. It was a lot of fun. So that's my talk. And yeah, I just wanted to say a huge thank you to the ESI for just being my home for for a couple of years, for 3 years. I miss it every day, and I'm not being hyperbolic, or extra. I really do miss everyone at the ESI very, very much. And a huge thank you to all my sponsors, NRF, COE, Durant Foundation, and PAST for making this sort of research possible. A big thank you to Tandy for helping me behind the scenes as well, get this research out there and helping with the press release and everything as well. I'm incredibly grateful. So thank you very much.